Yeah. So let us start with a brief discussion of scalars, vectors, and tensors and their notation. Okay, so they have a distinct set of notations that one needs to follow. So what are scalars? I mean, everyone knows scalars are entities which just have a magnitude. Okay, so they are entities which do not have any directionality. Vectors, in the most trivial sense, something which have magnitude and direction. I mean, this is not at all a good definition for a vector, but anyway, it works. For engineering, it works. And tensors are something which have both magnitude and they have two directions. One is the areal direction and one is the forcing direction. I mean, I'm just writing the area and forcing with respect to stress. We'll come to the detailed discussions of this. But just remember that tensors have two directions, vectors have one direction, scalars have no direction. Okay. And fluid mechanics, you will encounter all these three quantities because uh, in order to describe a complicated phenomenon, one needs to actually have all the different mechanisms and toolkits available, without which it's not easy to make mathematical progress. Yes? Anyone? Okay. So if anyone has any doubt, just uh, let us know and we'll look into it.
So could you increase the thickness of the pen?
It's at maximum.
Okay.
Is it coming too small?
It's thinning out, sir, a little, but it's all right. I mean, we can manage.
Let me see if there is some other. Let us look into it because it's a perennial thing, right? So stylus, no. Screen, no. View, mouse. Yeah. No, I mean they don't allow you to.
Change the background by white color. Black.
You want it to be white.
Yes,
Okay, that's fine. Okay, let me see. Does this work?
yes, yes.
This is okay?
Yeah, yes,
Yes.
sir, yes, sir.
Okay, good. So it's super thick. Anyway, so okay. So scalars are just quantities, right? So things like pressure, temperature, density. So these are scalars. What about vectors? So let's say we have a position vector x, and we can write the position vector in terms of its components. So in fluid mechanics, we make use of indices like 1, 2, and 3 to represent axis x, y, and z. Okay. So normally you would use I, j, k as the basis vectors, right? But in fluid mechanics, you would use E1, E2, and E3 as the basis vectors. Or equivalently, you can use Ex, Ey, Ez as the basis vectors. So the quantity x would be written as x1 e1 plus x2 e2 plus x3 e3, where x1, x2, x3 are the components of x in the directions e1, e2, and e3. So if this were a Cartesian simple thing that you would, write it down as you would do in 11th, 12th, or first year, it would be xi plus yj plus zk. But we don't like to use x, y, and z, where it's x1, x2, x3, and so on. So we represent any vector in this particular form, and the unit vectors are this. So unit vector e1 will be 1 0 0, unit vector e2 will be 0 1 0, unit vector e3 will be 0 0 1. Okay, so these will be the unit vectors. So in a shorthand notation, we can represent a vector. So suppose let us write down a vector A. So it is A1 E1 plus A2 E2 plus A3 E3. So this is what we discussed above, but we can equivalently write it as summation of AI EI, I going from 1 to 3. So this is called as a indicial notation or index notation. This thing is called as the full vector notation. And in fact, there is something called as the Einstein summation notation. So if you have two indices which repeat, so here the index I repeats twice. So instead of writing the summation, we can drop the summation. So we can simply write it as AI EI. So the summation is implicit. And this is called as the Einstein notation. Can someone guess why Einstein was so much interested with all this?
Sir, I read a story that once a woman asked Einstein why the tea, when they stirred it,
Okay.
why the sugar wasn't stirred. So I guess he looked into fluid mechanics.
Well, that's a very weird anecdote, but so the real deal is Einstein did a lot of fluid mechanics as his bachelor when in his during his bachelor days. So his thesis was actually on Stokes flows. So there is a class of flow called as Stokes flows, particulate flows, where you analyze the effect of having multiple particles in your flow. So there is a very famous formula called as Stokes Einstein relationship. Okay, it's called as a Stokes Einstein, and his PhD thesis, in fact, was on particulate viscosities.
Sir, there was something on Brownian motion only,
Yeah.
right?
So this particulate viscosity and all that was a part of his thesis, which included Brownian motion also. So viscosity, he tried to relate how viscosity relates to the Brownian motion of a particle. Okay, the relationship between the diffusion and viscosity. That is exactly what this relationship is. Good. So actually, his son also is a. I mean, I don't know whether he's still there, but his son did a lot of work on hydrology. Hydrology refers to the motion of fluids under the surface of the earth. It is extremely complicated. Let me tell you this much. It is also one of my areas of research, and hydrology is coming up to be a big uh, field of research nowadays because of the huge stress on groundwater that humans are putting. Understanding the pumping consequences of water, industrial consequences of drawing too much water, and so on. It's extremely difficult for us to sustain life without having a clear understanding of groundwater transport and how climate gets associated with groundwater transport. So anyway, let's continue. Oh, by the way, at the end of the lecture, we'll look at certain non-intuitive ways in which fluids and electric fields can interact. Someone asked me through an email. So at the end of this class, I mean, this class will not be very large. Most of it will be easy, and you can do it as a homework. So this is called as the Einstein summation index, because if you have index repeating, you just sort of drop the summation sign. So let us write down what this index would look like for a dot product. So what is A dot B? So if I write down A vector as AI A1 B E1 plus A2 E2 plus A3 E3 and B as B1 E1 plus B2 E2 plus B3 E3. So what will be A dot B?
AI.
A1 B1
So let us write down the full thing. So A1 B1 plus A2 B2 plus A3 B3, and it is essentially summation of AI BI I going from 1 to 3, right? And in Einstein summation index we can write this as AI BI. Very good. Now let us write down the formula for divergence of a vector. So divergence of a vector, what is it? What is it going to be? Okay, so before you tell me the answer, let me write down the gradient operator or the divergence operator. It will be del x 1 E1 plus del x2 E2 plus del x3 E3, right? Instead of x, y and z, you will have x1, x2, x3. So keeping this operator in mind, what will be this expression?
if A1, A2, A3 are constants, so 0.
No, not constant. We'll write it in terms of A1, A2,
Del
A3.
AI, del AI, del XI.
So it will be del A1, del x1.
Del A1 by del X1 E1. Yes.
No, there won't be any E1 anymore. Because see, divergence of a vector is a scalar.
Yeah, got it.
Please remember that divergence is a scalar. Gradient is going to be a vector. We'll go into gradient also. So this is nothing but summation del AI, del xi, and I equal to 1 to 3. And because the index I is repeating, like here the index I was repeating, since the index I is repeating, we can write this as del AI, del xi. So what about gradient? Let us write down the gradient of a scalar, say phi. Okay, so this will be del phi del x1 ei e1 plus del phi del x2 e2 plus del phi del x3 e3, which is nothing but summation of del xi phi ei, I going from 1 to 3, right? So again the index I is repeating twice, and thus I can simply write it down as del phi del xi ei. So the summation is implicit. Okay, so it's a very simple thing to write down in index notation, and by the time we come to the definition of tensors and all, we'll come into the way we can write down the curl of a vector and all that. But let us come to a more rigorous definition of a vector, that is rotation. A vector is something which must obey certain rotation properties. So let us go to a new page, and or rather let us keep it on this page because there's plenty of space left. So rotation of axis. What do you think a rotation of axis does to a vector? Who can tell me this? I mean, think about it and tell me, what do you think the rotation of an axis does to a physical vector. So let's say like velocity or displacement or something.
So it can change components of that vector.
It can change the components of that vector, but fundamentally it cannot change the vector itself. Fundamentally, it cannot change the quantity itself. Meaning, let me draw a coordinate system. In this particular coordinate system, right, if I have this particular velocity, and if I take another coordinate system like this, has the velocity changed? The components have changed, but the actual vector itself has not changed. Okay, the magnitude and direction of this entity has not changed. Okay, so rotation of axis will only change components. And how does the component change? That is the question we want to answer. And that how a component changes is actually the difference between a vector and a pseudo vector. Okay, so how it actually changes is the difference between a vector and a pseudo vector. It sounds very science fiction like, but that is what it's called. So let us write down in a given coordinate system. Let us write down in a given coordinate system a vector u, or in fact let us call it as x only, just to keep it consistent. So x is like a displacement vector. Okay, so displacement vector in one coordinate system is x1 e1 plus x2 e2 plus x3 e3. In a separate coordinate system, x can be also written as x1 prime e1 prime plus x2 prime e2 prime plus x3 prime e3 prime, where this particular yellow coordinate system is e1 e2 e3 and e1 prime e2 prime e3 prime. Okay, so regardless of the coordinate system, okay, the vector itself does not change, but the components of the vector do change, like someone had already mentioned. So now we want to know the relationship between the primed components, that is the components in the primed coordinate system, compared to the components of the original coordinate system. So how can we do that? So E1, E2, E3 are orthogonal bases. What do you mean by ortho? Oh,
perpendicular to each other.
they are perpendicular to each other, yes. Meaning E1 dot E2 is 0. I mean, I'm forgetting the arrows, but you should be clever enough to understand. And E1 dot E3 is also going to be 0. Actually, how can you write this in a vector form? So, EI dot EJ will be 0 when J not equal to I. When J equal to I, it will be 1, right? When J equal to I, it will be 1. So anyway, uh, so they are said to be orthogonal, meaning that I can utilize orthogonality to sort of arrive at the expressions that I desire. So how can we do that? Let us see. Let us see. It's rather straightforward, and probably some of you might have figured out by now how to do that. So x1 prime e1 prime plus x2 prime e2 prime plus x3 prime e3 prime is equal to x1 e1 plus x2 e2 plus x3 e3. This is what we have. If I want to isolate e1 from the left hand side, how will I do that? I just want everything else to vanish on the left, and I just want the component, not e1, rather component of e1. I just want x1 prime to be existent in the left hand side.
Dot product with T1 prime.
So take a dot product with e1 prime. So x1 prime e1 prime dot e1 prime plus x2 prime e2 prime dot e1 prime plus x3 prime e3 prime dot e1 prime is equal to x1 e1 dot e1 prime plus x2 e2 dot e1 prime plus x3 e3 dot e1 prime. Because of orthogonality, this term will vanish and this term will vanish. Essentially, and this term will be 1. So x1 prime will be equal to x1 e1 dot e1 prime plus x2 e2 dot e2 e1 prime plus x3 e3 dot e1 prime. So in a summation form, we can write it as summation of xi ei dot e1 prime. Do you agree with this expression? And in Einstein summation, I can write this as x1 prime is equal to xi ei e1 dot e1. Okay. So essentially, this entire vector dot with e1 prime. Sorry, should be e1 prime. Now we chose to find out the first term of this. So in this, we were interested in the first component. So the second component, what will it be? X2 prime, what will it be?
Same, this the dot product dot T2 prime.
Right? And what about x3? Same thing. So in a matrix form, I can write it as this. So x1 prime, x2 prime, x3 prime is equal to something multiplied by x1, x2, x3. What will this something be? So let us look at this expression. So x1 prime is equal to e1 prime x1 plus e2 e1 prime x2 plus e3 e1 prime x3. So what will be this component?
E1
even dot even prime.
So let me just take this over here. Okay, so this will be E1 prime dot E1. This will be E1 prime dot E2. This will be E1 prime dot E3, right? Because dot product is commutative, right? Dot product is commutative, I can do this. What about this term?
E2 prime dot E1.
So E2 prime dot E1, E2 prime dot E2, E2 prime dot E3. Similarly, E3 prime dot E1, E3 prime dot E2, and E3 prime dot E3. So this particular matrix is called as the matrix of direction cosines. Because all the components are nothing but direction cosines, right? These are nothing but the direction cosines between the first coordinate system 1, 2, 3 and the second coordinate system 1 prime, 2 prime, 3 prime. Do you agree? Is it okay? Is the interpretation okay? So this is also called as the rotation matrix. Okay, and in a shorter notation, I can write down xj prime as xi cij.
Excuse me, sir.
Yes,
While deriving the equation, you equated both the vectors. Is
yes.
it true?
Yes, it is always true because the vector itself will never change. The magnitude and direction of a vector does not depend on your choice of coordinate system. Okay. So, for example, if a bird is flying towards the south, it doesn't matter whether I am seeing it from my viewpoint or whether someone else is sitting on a building and viewing the bird. All we will see are different projections of the bird, but the bird actually is flying in that direction. Do you understand?
Yes.
So the vector itself never changes. What changes is the components of the vector in the particular coordinate system that you are looking at. And our question is, can we relate the components of the vectors that I see in my coordinate system with the components of the vector you see in your coordinate system? Okay. So the rotation matrix components are called as Cij. Okay, and Cij is defined as Ei dot Ej prime. Cij is defined as Ei dot Ej prime. So if it is defined as this, xj prime is equal to xi Cij. So let us expand this. Let us see how this notation is. So it is xi Ei dot Ej prime, which is nothing but x1 e1 dot ej prime plus x2 e2 dot ej prime plus x3 e3 dot ej prime. So it is, if you just put j equal to 1, you will confirm the original expression that we had written, right? This thing. Just choose j equal to 2. Just choose j equal to 2, right? So then we have ei ej prime e2 e2 prime e3 e2 prime multiplied by x1 x2 x3. So just convince yourself this is true. Okay. So this is the definition of a vector. Entity is a vector if its components obey rotation law given by this. Okay. The component of the vector must satisfy this rotation law. Why is there such a silence?
Yes, sir.
Yes, clear, clear.
Okay.
Yes.
Okay, good.
Hello, sir.
Yes,
Can we say CIJ as a matrix of linear transformation?
exactly. So I was going to say that. So essentially, Cij is a matrix which transforms x1, x2, x3 into x1 prime, x2 prime, x3. And that transformation is by means of a rotation. Very good. So very good. I'm quite happy that you guys are telling things on your own. It's quite rare. So good. So that is indeed correct. Please go home and not. I mean, don't go home and see this again. You're already at your home. So just see this again or read this again sometime. I'll tell you the reading material also. Okay. Okay. So let us move on to multiplication of matrices. So multiplication. Excuse me, I have a phone call. Nothing important. So let us move on to multiplication of matrices. So let us consider two small matrices. I mean abstract matrices. We don't write down the values. So to find out the product of this, so the product of this, what will be this component? This component will be this row multiplied by this column, right? This component will be this row multiplied by this column, and this component will be this row multiplied by this column. Do you agree? I mean, this is straightforward.
Yes, sir. Yes, sir.
Yes, sir.
So how do you write it down in an index notation? So suppose I want to write that A. So to write down matrix, you just put double dash on top of it. So A double dash is equal to B times C. So how do you write it down? So first of all, in order to write it down in a symbolic or a index notation, I must refer to some ij component of A. Okay. So ith row and jth column. Okay. So what will be the ith row and jth column of A in terms of B and C? So it will be summation of Bik Ck J, K going from 1 to 3. So this is what the summation, I mean, I don't know if you have done this in programming class. This is how we used to do it in our first year PDS lab. So do a for loop for I equal to this, for j equal to this. Then inside that for loop, you need to have a k loop. Okay. Essentially, this is that encoding.
Yes, sir. Actually, we did this.
Okay. So this is the index form of writing it. And the Einstein notation form would be simply Aij would be equal to Bik Ckg. Because k is repeated, that summation is implicit. Actually, Einstein went ahead to do a lot of work on general relativity where you need to have a lot of tensorial operations, space-time and all that. So, in order to do all those, you really don't want to keep doing the summation business. That is why he dropped all the summation. It's called as summation index. Okay, so let us move on to tensors. So tensors are essentially entities which have magnitude and two directions. It's a very weird way of defining it, but let me give you a concrete example. So consider, uh, I think you have done this in your first year mechanics course as well. So if this is 1, if this is 2, if this is 3, the directions I mean. So this is E1, E2, E3. So what are the forces acting on this particular face? On this particular face, you can have a normal force like this, or you can have a shear force like this, right? Or like this.
Yes.
So how do we tell that that force is a normal or a shear force? So how do you make this distinction?
If it is perpendicular to that surface,
Okay, so we need an aerial vector.
Yeah.
So with respect to this area vector, we need to sort of look at how the force is. So let me just rub this up. So the area vector is pointing out like this. So the area vector points in the one direction. Okay. And the force when it acts on the one direction, that particular stress component is called as tau 11. So tau 11 meaning that the force is acting on a face, acting which on a face which points in the one direction. So the first index is the area vector, and the second index is the direction of force. Pardon me. Okay. Okay. So similarly, what will be this? What component of stress will be this?
Tau 12.
Good. So it is tau 12 because one is the area direction, area direction, and 2 is the direction of the force. So with this we can sort of construct the stress tensor. So tau 11, tau 12, tau 13, tau 21, tau 22, tau 23, tau 31, tau 32, tau 33. So these are the 9 stress components which can completely define the state of stress on a given element, right? But like we did for vectors, can we also construct a rotation rule for this?
Yes, sir.
So of course we can, but do you know it? I don't know how you said yes, but obviously we can.
we will define force in terms of
This side.
Hmm?
Sir, we did that for like in the Moore circle, so we could do that something similar in 3D.
So that more circle thing only you have to do. That more circle thing that you had done is exactly what it is. So more circle, the theoretical foundation of more circles is from transformations, nothing else. Okay. If you do all this in 2 dimensions, and see in 2 dimensions you will end up with tau 1 1 prime, tau 2 2 prime, and tau 1 2 prime in terms of tau 1 1, tau 2 2, tau 1 2, and cos theta sin theta terms. Okay. And when you sort of try to eliminate cos theta sin theta using trigonometry, you end up with equations of circle. That leads to a Moore circle. Graphically, when you do all that, it becomes a Moore circle. So I'm very happy. So you take it as a small homework. Okay. Find out rotation law for a tensor, in particular tau ij. In fact, let me tell you the answer. So tau mn, tau prime mn, which is the component in the rotated coordinate system, will be equal to summation CIM C Jn tau ij, where I goes from 1 to 3, j goes from 1 to 3, and this C is the same matrix. Okay, Cij was defined as Ei dot Ej in the two coordinate systems. So you take it as a homework. So if you drop the summations, because I is repeating twice and j is repeating twice, so it becomes CIM CJN tau ij. And if you want to write it in terms of symbols, in matrix multiplication symbols, so essentially it is what CIM, this transpose multiplied by C, multiplied, rather not transpose like this, it will be CMI transpose tau ij CJN. So essentially it will be C transpose tau C. Symbolically, tau prime will be equal to C transpose CT. And if you ever go into a career in continuum mechanics, solid mechanics, fluid mechanics, you will keep on seeing this kind of transformation. In fact, even for graphics and all, you will see this kind of transformations, because 3D transformations are pervasive in 3D graphics as well. Okay. So
Sir, is refractive index a tensor?
it's a difficult question to answer, for me at least. I cannot really comment on that. I used to think it was a scalar.
No, sir, but refractive index can vary different direction. Like if the arrangement of the like the lattice is such that
Okay, okay. So if it has anisotropy, then you can of course. So if it so let me just show you a small trick. If I have a tensor and I want to make it from, so I want to sort of e- encode the information of a scalar inside a tensor. How can I do that? So I just take a unit tensor and I multiply it with the refractive index. So in all the three primary directions, so these are sort of the diagonal elements and these are the primary directions, I multiply everything by this. And if I want to make anisotropy, so I just have mu1, mu2, mu3 as three principal components. But like you said, anisotropy, because of the lattice and all, it will lead to these non-diagonal components also coming into the picture. Okay. So in that case, yes, if it does happen like that, then it will actually be a tensor. I mean, I can tell you that heat conductivity, viscosity, all these things are actually tensors. let us look into some more small properties of tensors before wrapping up. One is contraction. Contraction of a tensor. So if I have a tensor Aij, okay, what is the contraction of the tensor? So it's called as a trace. Have you come across this? What is the
Yes, yes.
trace of a matrix?
The sum of
Some
the
of
that
the diagonal elements.
So tell me the expression for this in terms of Einstein summation.
AI.
Yeah.
So it will be AII. Very good. Acha, tell me this. If I have a Kronecker delta, have you come across the word Kronecker delta?
is
So it is nothing but this. So delta is 1, 1, 1. So what is the trace of the Kronecker delta? Exactly, it will be equal to 3. Good.
Sir, what is Kronecker delta?
So Kronecker delta is defined as delta ij it's a matrix delta ij which is equal to 1 if I equal to j and 0 if I not equal to j. So this is the
Identity net.
it's basically an identity matrix. So in all the diagonal components I equal to j because this is delta 1 1 delta 2 2 delta 3 3, but for all these things it is delta 1 2 delta 2 3, so it is 0. Okay. Okay, so other things I'll just put them in homework, not really discussion stuff. In the next,
first.
yeah,
Towards the beginning of you actually said that uh, when you were talking about the rotation law for vectors, you talked about pseudo vectors. I
Hmm.
haven't heard that before.
So rotation things which involve curls and all these things, they are called as pseudo. So for example, if you look at a rotating fan from one side of the fan, the rotation sense will appear in one direction. But if you look at the rotation sense of the fan from the other side of the fan rotation sense will appear to be opposite. So basically
Yes.
the rotation vector, which is like the axial vector of the fan, will appear to be changing directions. Okay. So those kind of entities which do not preserve their components. So basically that minus sign comes in. So instead of having xi prime equal to Cij xi, you will have a minus sign coming in. So then that becomes a pseudo vector. Actually, for various mathematical tips and tricks in fluid mechanics itself, it's a very useful thing to know. And then in due course, if we ever find enough time, we will cover it. Okay, we'll also cover it. Acha, let me just cover one more small concept really quick because I think you might have covered this in solid mechanics also. A tetrahedron, the forces acting on a tetrahedron. Have you done this? Consider the face of this tetrahedron pointing in the n direction, and the force is not collinear with the normal vector, but it is something like this. So have you done this calculation?
No, sir.
What is the force in terms of the
No.
stresses? What is the relationship between the force and the stress? No, right? Anyway, so we'll do it in the regular class, not in today's class. Okay. This is slightly important for us to do it in regular class. So okay, we discussed Kronecker delta, but we did not discuss one more important matrix, In today's class, because it's slightly a general discussion, let's quickly discuss alternating tensor. It is the only third order tensor I know of practical use. It's called as epsilon ijk. So it's a third order tensor, meaning it has 9 components. So stress, sorry, not 9 components. So it has how many components? 3 cross 3 cross 27 components. Okay. So what is it actually? So like we defined delta ij as 1 if I equal to j and 0 if I not equal to j. So epsilon ijk is defined as 1 if ijk are cyclic, minus 1 if ijk are anticyclic, and 0 if any index I, j or k repeat. Meaning epsilon 1 2 3 is going to be 1, epsilon 2 1 3 is going to be minus 1, epsilon 1 1 3 is going to be 0. So cyclic meaning 1 2 3, 1 2 3. So if you maintain this cycle, so similarly epsilon 3 1 2 is also 1, epsilon 2 3 1 is also 1. Okay, so these are all equal to 1. So anything you think anticyclic, okay, like 2 1 3 3 2 1, okay, 1 3 2, so that's going to be minus 1. Epsilon 1 1 3 is, because I have repeated one index, is going to be 0. And with the help of this, alternating tensor, we can find out a very useful shortcut of writing down a cross product. Okay, a cross product A cross B. So the kth component of A cross B is equal to epsilon I j k A I B j. This is what I'm telling you. Let us verify this. Let us do the old boring way, the cross product. So I j k A1 A2 A3 B1 B2 B3. So don't confuse with this k and this k. Okay. So to prevent that confusion, let me just do here E1 E2 E3. Okay. So what is the E1 component? A2 B3 minus A3 B2, right? Has everyone left?
Yes, sir.
How many people are there in
No,
the
sir.
class?
No, sir, we are here. We are here, sir.
Okay. Thanks for reassuring. Oh, there's a lot of people here. Good. I thought everyone left. So let us verify this. Let us verify this. Let me create a new page. I don't know whether you're finding all this boring, because I think you've done all this before also. The chance you may find this boring. So I want to know what the first component of this cross product will be. Right? So this is the one component of the cross product. So if I put k equal to 1, I should be able to get the first component of this cross product. So put k equal to 1. So A cross B's first component is going to be, so let me substitute k over here. So epsilon I j1 ai bj. So now I j repeats. So essentially it's going to be summation I equal to 1 to 3 j equal to 1 to 3 epsilon I j1 ai bj. Now look, because 1 already appears over here, I and j cannot be 1 anymore. Do you agree? Because by definition
Yes, sir.
of alternating tensor, if I and j repeat, this whole thing will become 0. So let's say I is equal to 2. So first term I equal to 2 wala term. This. So it will be epsilon 2 j 1 a 2 bj. This is I equal to 2, and I equal to 3 will be epsilon 3 j1 a3 bj. And let us not forget the summation of j equal to 1 to 3 still exists. I have essentially just expanded this particular I equal to 1 to 3, but I have left out I equal to 1. Is it clear?
Yes.
Now I have these two terms. Okay, now in this term, look, 1 already exists, 2 already exists. So j cannot be 1 or 2.
Hmm.
J cannot be 1 or 2, so j can only be 3. So out of this summation, only j equal to 3 will remain. Epsilon 2, 3, 1, A2, B3. Out of this, what will remain?
That 2.
So 2 will remain. So epsilon 3, 2, 1, A3, B2. Now look, what is the cyclicity? So what is epsilon 2, 3, 1? 2, 3, 1 is cyclic, but 3, 2, 1 is anticyclic. So this, so 2, 3, 1 is cyclic, so this will be A2, B3, and this will be minus A3, B2. So the first component of the cross product from the indicial notation is A2B3 minus A3B2, which is the same as our boring method, A2B3 minus A3B2. Are you convinced?
Yes.
Yes, sir.
Or should we do it for the second component as well? In fact, let me put it as a small homework. Do it for the second component as well. Second, third. There is one more very specialized relationship between the alternating tensor and the Kronecker delta, and that particular relationship, I'll be very happy if you can do it on your own. That is called as the epsilon delta relationship. It is called as the epsilon delta relationship, and let me write it down. Epsilon ijk epsilon klm is equal to delta il delta jm minus delta im delta jl. So try to prove this also. I will not give you any hints because it will ruin your fun. Try to prove this. I mean, it's not super essential to prove this, but in your free time, try to prove it. Okay, so we have covered some certain aspects of all these things, cross products and all, in terms of indicial notation. So in the next class, we'll look at some more curls and symmetric, antisymmetric tensors, why it is important for us to know. Eigenvectors and all you already know. We'll look at just the basics of Gauss theorem and Stokes law, Stokes theorem, not Stokes law. Okay, we'll look at all those, and that will bring us to the end of the mathematical preliminaries. Next, from after that next class, we'll start doing fluid kinematics. In fact, not that. We'll start off with hydrostatics. We'll cover 4 classes of hydrostatics. Then after that, we'll cover 4 classes of kinematics of flows, and then let's see how it proceeds. Okay. So I'll see you guys on Wednesday, and hopefully I'll have an assignment ready for you tonight. I have a lot of other work as well. So let me stop recording. As usual, that recording